When a utility company replaces a transformer with a larger unit, the available fault current at the customer's service entrance can increase. If the existing customer service equipment, specifically its ampere interrupting capacity or AIC rating, is insufficient to handle this new higher fault current, a potentially dangerous situation arises. The question of who bears the financial responsibility for upgrading the customer's service equipment then becomes pertinent. Generally, the utility company is held responsible for covering the cost of upgrading the customer's service. This responsibility stems from the utility's obligation to provide safe and reliable electrical service to its customers. By increasing the available fault current, the utility alters the electrical environment the customer's equipment is subjected to. The installation of a larger transformer, while potentially beneficial for grid capacity or reliability, can inadvertently create a safety hazard if the customer's equipment is not rated to withstand the increased fault current. A fault current is the magnitude of overcurrent that occurs during a short-circuit condition. The available fault current is determined by the source impedance of the power supply, which in this case is the utility's transformer, and the impedance of the circuit up to the point of the fault. A higher capacity transformer typically has a lower impedance, resulting in a higher available fault current. The AIC rating, expressed in amps, represents the maximum fault current that an electrical component, such as a circuit breaker or panel board, can safely interrupt without failing catastrophically. If the available fault current exceeds the AIC rating of the equipment may rupture, ignite, or otherwise fail dangerously during a fault. Therefore, it is crucial that all electrical equipment installed in a system have an AIC rating equal to or greater than the available fault current at its point of installation. Utility companies typically operate under tariffs, which are documents that outline the terms and conditions for providing electrical service to customers. These tariffs are often regulated by public utility commissions or similar governing bodies. The tariffs usually address issues of service upgrades, equipment ownership, and responsibility for maintenance and repairs. In many jurisdictions, utility tariffs include provisions that address situations where the utility's actions necessitate upgrades to customer equipment. These provisions often place the financial burden of the upgrade on the utility, particularly when the upgrade is directly caused by the utility's changes to the electrical supply. The rationale behind this assignment of responsibility is that the utility is in the best position to assess and mitigate the potential risks associated with changes to the electrical system. The utility has the expertise and resources to calculate the available fault current at various points in the system and to ensure that customer equipment is adequately protected. Furthermore, holding the utility responsible for upgrade costs incentivizes them to carefully consider the impact of their actions on customer equipment and to take steps to minimize any potential negative consequences. In situations where a utility upgrades a transformer, it is standard practice for the utility to conduct a fault current study to determine the impact of the upgrade on the available fault current at customer service entrances. This study involves calculating the expected fault current at various points in the system, taking into account the impedance of the transformer, the distribution lines, and the customer's wiring. If the fault current study reveals that the available fault current will exceed the AIC rating of existing customer equipment, the utility is typically obligated to take corrective action. This may involve upgrading the customer's service entrance equipment, such as the main breaker panel, to a higher AIC rating. Alternatively, the utility may install current limiting devices, such as fuses or reactors, to reduce the available fault current at the customer's service entrance. The specific measures taken will depend on the particular circumstances of the situation, including the magnitude of the fault current increase, the cost of the various mitigation options, and the utility's policies and procedures. In cases where the utility is responsible for upgrading the customer service, the utility will typically work with a qualified electrical contractor to perform the upgrade. The contractor will assess the existing equipment, determine the required AIC rating for the new equipment, and install the new equipment in accordance with applicable electrical codes and standards. The utility will typically pay for the cost of the upgrade, including the cost of the equipment, the labor, and any necessary permits or inspections. It is important to note that the specific terms and conditions governing utility responsibility for fault current upgrades may vary depending on the jurisdiction and the utility's tariff. Therefore, it is essential to consult the applicable tariff and any relevant regulations to determine the utility's obligations in a particular situation. In addition to the tariff, other factors may also influence the determination of responsibility. For example, if the customer's equipment was already inadequate before the utility's upgrade, the utility may argue that it is not solely responsible for the upgrade costs. Similarly, if the customer has made modifications to their electrical system without the utility's approval, the utility may argue that the customer is responsible for any resulting problems. However, in most cases, the utility will bear the primary responsibility for ensuring the customer equipment is adequately protected against fault currents, particularly when the utility's actions have increased the risk of a fault. The National Electrical Code, or NEC, provides guidelines for electrical installations and safety. While it doesn't explicitly dictate who pays for upgrades due to increased fault current, it does mandate that all electrical equipment be rated for the available fault current at its point of installation. This implicitly supports the utility's responsibility, as their actions necessitate the upgrade to meet NEC requirements. Article 110.9 of the NEC addresses interrupting rating. It states that equipment intended to interrupt current at fault levels shall have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Equipment intended to interrupt current at other than fault levels shall have an interrupting rating at nominal circuit voltage sufficient for the current that must be interrupted. In simpler terms, this means that all electrical equipment, such as circuit breakers, fuses, and switches, must be able to safely interrupt the maximum fault current that could occur at their location in the electrical system. The interrupting rating of the equipment must be equal to or greater than the available fault current. Article 110.10 addresses circuit impedance, short circuit current ratings, and other characteristics. This section requires that the overcurrent protective devices, the total impedance, the component short circuit current ratings, and other characteristics of the circuit to be protected shall be selected and coordinated to permit the circuit protective devices used to clear a fault to do so without extensive damage to the electrical equipment of the circuit. This means that the electrical system must be designed and installed in such a way that a fault will be quickly and safely cleared by the overcurrent protective devices, such as circuit breakers and fuses. The system must also be designed to prevent damage to the electrical equipment during a fault. The NEC also provides guidance on calculating fault currents. Article 110.24 requires that service equipment in other than dwelling units shall be legibly marked in the field with the available fault current. This marking provides information to electricians and other qualified personnel about the potential fault current at the service equipment. This information is essential for selecting and installing equipment with the appropriate interrupting rating. Annex of the NEC provides detailed information on calculating fault current. This annex includes formulas and examples that can be used to determine the available fault current at various points in an electrical system. The calculations take into account the impedance of the utility transformer, the service conductors, and the branch circuit conductors. These calculations can be complex, and it is often necessary to use specialized software to perform them accurately. To ensure compliance with the NEC, it is essential to have a thorough understanding of fault current calculations. Electricians and engineers should be trained in the proper methods for calculating fault currents and for selecting equipment with the appropriate interrupting rating. Failure to comply with the NEC can result in serious safety hazards, including electrical shock, fire, and equipment damage. The utility company's role in this process is paramount. They are responsible for providing the necessary information about the available fault current at the service entrance. They should also be willing to work with customers and electrical contractors to ensure that the customer's equipment is adequately protected. In summary, when a utility company upgrades a transformer and increases the available fault current, they are generally responsible for ensuring that the customer's equipment can handle the new fault current levels. This responsibility is based on the utility's obligation to provide safe and reliable electrical service and on the provisions of the applicable utility tariff. The NEC also plays a role in this process by requiring that all electrical equipment be rated for the available fault current at its point of installation. The utility should conduct a fault current study to determine the impact of the upgrade on the available fault current at customer service entrances. If the fault current study reveals that the available fault current will exceed the AIC rating of existing customer equipment, the utility is typically obligated to take corrective action. This may involve upgrading the customer's service entrance equipment or installing current limiting devices. The utility will typically pay for the cost of the upgrade. It is essential to consult the applicable tariff and any relevant regulations to determine the utility's obligations in a particular situation. Electricians and engineers should be trained in the proper methods for calculating fault currents and for selecting equipment with the appropriate interrupting rating. The NEC provides guidance on electrical installations and safety, and it mandates that all electrical equipment be rated for the available fault current at its point of installation. This implicitly supports the utility's responsibility, as their actions necessitate the upgrade to meet NEC requirements. By adhering to these principles, utilities can ensure that their customers are protected from the hazards of fault currents and that the electrical system operates safely and reliably. Furthermore, good communication and collaboration between the utility, the customer, and the electrical contractor are essential for a successful upgrade. The utility should provide clear and timely information about the upgrade and its potential impact on the customer's equipment. The customer should be informed about the need for an upgrade and the reasons why it is necessary. The electrical contractor should be qualified and experienced in performing fault current studies and in installing equipment with the appropriate interrupting rating. By working together, these parties can ensure that the upgrade is completed safely and efficiently and that the customer's electrical system is adequately protected. Firstly, utilities must prioritize safety when modifying their infrastructure. Secondly, clearly defined tariffs and regulations are crucial for outlining responsibilities. Thirdly, proactive fault current studies are essential to identify potential issues. Fourthly, collaboration between utilities, customers, and contractors ensures successful upgrades. Fifthly, compliance with the NEC is paramount for electrical safety. All of these contribute to a safe and reliable electrical system for everyone.